We'll start our discussion with policy evaluation. And I want to remind you of that actor-critic method that we talked about. So we have an actor that gives you a policy mu k, and we have a critic which evaluates the policy mu k and gives you two options. Either it computes v mu k or it computes jk, which is an approximation to the value function. Okay, so this is a policy evaluator. Okay, so in the previous lectures, what we were talking about is how do you emulate value iteration algorithm? How do you emulate that using samples? Okay, so you don't have the actual system, or the actual system is too big. You're not able to compute the value iteration at every point of time. Then the question was, how do you use samples in order to estimate the value iteration algorithm? And we talked about Q-learning, we talked about SARSA. So SARSA was on policy, Q-learning was off policy. And we talked about empirical dynamic programming, and we talked about asynchronous algorithms. Okay, so all of those were different types of algorithms that were trying to emulate value iteration algorithm using simulation-based techniques. Now we are going to talk about actor-critic methods, where the actor is just an optimization method. So remember what actor does. So actor's job is to generate mu k from jk minus 1. So this is your arg min over all policy mu of expected value of c plus alpha jk minus 1. So it uses the previous estimate of the policy, estimate of the value function, adds the current cost, uses the discount factor, and generates a new policy mu k, which is the arg min over all possible policies. Okay? Yes.
Is there any difference when you write v or j? Are those just?
Yeah, so it's different. So v is value function of mu k, exact value function of mu k, whereas j is an approximation of the v. Okay, so that's typically how we differentiate between what is an approximation with what actually is the true value.
It's like, because last time when you did the empirical one, you defined the.
So yeah, I should have written v hat or something. Yeah, it's.
Well, yeah. So, but why not j?
That's because I'm picking different references, so different references have different notation. So I have not thought about all the notations for.
So j is like a v hat.
J is like a. Okay, so let's go to this particular book. Okay, so v hat still remains a random value function. It's still a random variable, random vector, whereas j is supposed to be the expected value of some. Okay.
It's not random.
It's not random. Yeah, j is not random. It's an expected value of something, and that something could be a complicated operator. Yeah. And when we talk about simulation-based technique, then everything becomes random. J becomes random, v hat becomes random, and so on. But that's where people tend to differentiate between these. Now, of course, if you look at papers, so modern papers versus older papers. So older papers differentiate between the value function, approximation to the value function, and random value function. The newer papers have no differentiation as such in their notation. And it becomes very difficult to read newer papers in reinforcement learning for that reason, because they don't differentiate between these things very clearly. Okay. So that's why I like reading older papers. It's easier to understand because the notation is set up correctly. Okay, so there's nothing much to talk about the actor case. So I don't know how many of you have taken a course in optimization, but those of you who have taken 5500 or 5759 would know how to solve optimization problems of this type. Those of you who have not taken, I highly encourage you to take it if you want to learn optimization. Okay, so this is something where you use gradient descent method, or you use some sort of Newton's method, gradient descent method, line search method, and so on in order to compute this argument. The goal for today is to actually solve this particular problem, which is you have, instead of the model of the system, now you have either a simulator from which you can generate trajectories, or you have a real world sample from, let's say, a web page or New York Times website or something like that. So you have a simulator or a website, and in the website or the simulator you can store the policy mu, and you give it an input I0, and you get an output well, I0, C0, I1, C1, and so on. Okay, so policy is how your website is laid out. Okay, so that could be like a real world situation where you pick a policy, which is how the layout of the website is or what the recommendation algorithm is. Or you have a simulator where you can simulate, for instance, you have a traffic simulator and you have a signal phase and timing policy, and you have picked that policy, you have encoded that policy in the simulator, and the simulator, you give it the input of the current state, the current queue length of the vehicles to the simulator, and it outputs what the waiting time for the people at the intersection is, and what the next queue length looks like, and what the waiting time for the people is, and what the next queue length looks like, and so on and so forth. Yes.
So last time you had mu, I guess u as an input.
That's right.
But
now the policy is fixed.
Policy to be in there.
Yeah, you want the policy to be fixed, and you just want to evaluate that policy. How good that, I mean, what the expected discounted cost for that particular policy looks like. So this is similar to the real world setting, because in real world setting, you don't change the policy every second or every minute. You probably keep the policy for a month or for 15 days. You look at what the response looks like, and then on that basis, you update the policy. Okay. So the question now is, using this data set, can we estimate V mu or J? Okay, I'm not writing J mu because J could be an approximation to V mu. Okay, some approximation to V mu. So this would be the case. This is the first algorithm I'll talk about, which is how do you estimate V mu. And the second algorithm will be TD lambda algorithm, where we will try to estimate J from this data set. Now there are two situations. One is you have a single website, or a single simulator, and you can only get one stream of data. Okay, so one sample path. So this is a single sample path. Alternatively, you have multiple such simulators. You can initialize using I0, let's say 0, I01, I02, and you get multiple sample paths. Yes.
Sorry, so in this case, so is the simulator random? Meaning like if I put in the exact same input IO.
You can get
to the
different
C-
sample paths.
Yeah.
Yeah.
So these different IOs are not necessarily the different states.
They could be the same state or they could be different states. You can initialize howsoever way you want. So in the first round, you have 5 people at 5 q length of vehicles at every intersection. In the second one, you will have 5, 3, 4, 2 number of vehicles at the intersection, and so on and so forth. So you can initialize it. This can be completely random and independent of each other. But this gives you a single sample path. So a sample path means that the simulator itself could be emitting a random trajectory, right? Because there are so many randomness happening in terms of cost and in terms of the next state transition. So you could have completely different. So no matter, even if you have the same initial input to the simulator, you can have completely different sample paths generated from the simulator. So how would you do this problem? Let's say we are in 1990s or 1980s. You are a PhD student at OSU or whatever, some university, MIT or some place, and this is the problem statement that's given to you. And I'll tell you the history of this. So by the way, this particular problem statement where you want to sample some value function from the data is not a new problem. It was actually used back in 1940s and 1950s in nuclear physics world, where they wanted to figure out how long a nuclear reaction is going to last or something like that, right? So at that point of time, people were studying problems of this type, and they called it Monte Carlo simulations or whatever at that point of time. So in physics community, people knew about these problems for a long time, and now we are reinforcement learning community. So we want to pick things from physics community and try to answer the same set of questions that physics people were asking. Okay. So what would you do? How would you solve this problem? Let's say our goal is to compute V mu, and V mu of I is given by expected value of summation t equals 0 to infinity alpha raised to t c of it mu it plus 1 given I0 equals to I. So this is the expectation that you need to compute. You can think of this as CT, in which case I can write it as expected value of summation alpha raised to t CT given I0 equals to I. Any thoughts? Yes.
Can we use the fixed point iteration and try to?
You can't really evaluate the fixed point, right? Because fixed point iteration requires you to be able to compute the expectation. And the problem is I don't have the model, so how do I compute the expectation?
Well, with a empirical average.
Exactly. So that's that's what my question was, right? So yes, go ahead.
You count every time the I of this in the sequence and it would forward to the whole sequence to get something.
Wonderful. So that's definitely a thought we'll keep in mind. So his point is we have finite number of states. Let's say we have 5 states. We have an infinite trajectory. So hopefully each state will be visited infinitely often in that infinite trajectory. And so I can truncate the trajectory whenever state I appears, and we can look at the cost moving forward from that particular trajectory. So we'll talk about that in a bit. But I think, let's say we don't have any problems with computational power, and I want to compute this expected value. What would you do? How would you compute the expected value? So remember, we have only the simulation result. So how do we compute expected value using simulation? So we talked about empirical averages in the previous lecture. So we'll do something similar. So a dumb way a dumb algorithm would be to pick V mu. You define let me cost estimate of the kth run starting from I is going to be summation of alpha raised to t, ct. T goes from 0 to infinity. For the kth simulator, so let me call it simulator 1, simulator 2, simulator k. So I pick the kth simulator, I look at this, I sum over k equals 1 to capital K, and then I divide it by capital K. Oh, this is cost estimate of k, kth run, so I don't have to do the averaging with respect to k yet. I'm going to do V mu of I, let's call it a hat, is equal to summation k equals 1 to capital K, cost estimate of k of I over capital K. Yes.
So this CT is the CT that came after I, all instances of I?
Yeah, so you start with initial condition. So I don't want to write I0, but this simulation K started with state I as initial state. So remember, we can pick the initial state here. So I pick initial state I and I run the simulation and I get these values of CT. So I'm denoting by superscript the simulation run. Like this is the kth simulation. I started with state I. I ran the kth simulation. I got these samples of CT. So this is not CT raised to K. Okay, maybe I'll write it in the bottom because I don't want you to confuse between this is alpha raised to T, but this is the kth run of the simulation and this is CT sample from the kth run of the simulation. So let me just keep everything in the subscript because we do need this alpha raised to T thing many a times. So we'll just keep it like that. Okay, so does this sound reasonable? So I start with initial state I run K simulations, I compute this discounted cost, and then I sum it over K times and divide it by capital K, and I get a sample estimate of V hat mu. It's a good estimate of V hat mu. And what else? You need to run infinite number of simulation, K number of times. So you have to have infinite trajectory K number of times starting with every state I in order to be able to compute this V mu of I. So the complexity is very high for this algorithm, right? We don't want very complex algorithm. So if your state is only 5, and if you want to truncate, remember there's a discount factor here, alpha raised to T. So perhaps you can truncate it at capital T when alpha raised to T is sufficiently small. And that could give you a good enough estimate of cost that you can use for computing V mu of I. So, okay, so now if we want to be a bit intelligent, I'm going to pick cost estimate summation T equals 0 to capital T alpha raised to T CTK. Okay, so this is a bit more intelligent because I know that alpha raised to T is 0.000001. So I don't really care about what happens after that. I'll just truncate it at capital T and I'll just live my life thereafter. Because anyways, I'm doing the estimation. I don't care about the true value. All I care about is an estimate of the value that's close enough to the true value. Okay, remember the goal in reinforcement learning is to compute mu star. I want to compute the optimal policy. So what I compute in the intermediate step, I don't really care much. As long as I get a good estimate, I'm good and it's good enough. I'll move forward and compute mu k plus 1. Okay, any problems you see with this particular algorithm? So now, if I have 5 states, I'll I'll use k rounds of simulation starting with each of the state, and I'll run it for capital T time step, and then I'll compute this estimate. So what's the problem with this algorithm? The problem is what happens when the number of states is very large. Okay, so now you need to have, so in this case you have k times the size of the state space. You have these many simulators needed. Now if the state space is very large, now you have to do a lot of simulation. So we want to be sample efficient. The situation is even worse in the real world setting. So you have only one New York Times website. You have only one New York Times website. So you literally have just one simulator. You don't have multiple simulators to run. And there are only 5 million people who will visit the website over the next 15 days. Okay, so you don't have the luxury of this capital T, picking the capital T. You have very limited number of capital T. So what do you do now? We have one website. We have only 5 million people who will come to visit that website over the next 15 days. So I want to be as sample efficient as possible in order to compute my v hat of mu. Okay, so how do we bring in that sample efficiency? So one of your friends noted that, look, if I have finite state setting, the states is probably visited multiple times. Okay, so let's look at what one trajectory is going to look like. Can I erase this side of the board? Any questions on this before I erase this? Okay. Okay, so now I want to be more sample efficient. So remember my trajectory, let's say my I0 was equal to 1 and I have 3 states. So maybe the S is 1, 2, 3. So I have only 3 states. Then my trajectory I0, I1, I capital T, this trajectory is going to look something like 1, 2, 3, 1, 1, 2, 2, 3, 3, 1, 3, 2, 3, and so on. So as you can see, 1 is visited multiple times, 1, 2, 3, 4. So I ran the simulation for capital T time steps. I get 1 4 times, I get 2 4 times, and I get 3 4 times. Wow, okay. This is an amazing simulation, okay? So I get the same state multiple times during my simulation, and I get the cost as well, C0, C1, C2, C3, C4. What is the discounted cost going from? So remember, what do I need to compute? So if I start from state I, what's the total discounted cost that I'm going to see? Okay, that's my problem. What's the expected discounted cost? So can someone tell me samples from, so samples of discounted cost from 1. So I have C0, alpha raised to 3, C3. No, sorry. So C0 summation alpha raised to t Ct. T goes from 0 to capital T. Then I have summation t equals to 3 to capital T alpha raised to t minus t Ct. Can someone tell me what the next sample looks like? T equals to 4 to capital T T minus 3 T minus 4 Ct. What else? Where else do I see 1? 9 to capital T alpha raised to t minus 9 Ct. So I have 4 samples of discounted cost starting from state 1. Okay, so I can call this cost estimate of MK1, cost estimate of maybe M. So kth simulation, right? So I'm doing one simulation. So this is just going to be 1. And this is going to be 1. This is going to be 2, 1 of 1. And this is cost estimate of 3, 1, 1, and so on. Okay, so from the same trajectory, from a single trajectory, I can get multiple estimates of the discounted cost. And then I'm going to compute my V mu of I, an estimate of V mu of I to be summation of M equals summation of k equals 1 to capital K, summation of M equals 1 to nk, cost estimate of M k I over summation of nk, k equals 1 to capital K. So nk is the number of times this state appears, 1 appears in the kth simulation, and I'm doing k number of simulations. So here I've just written simulation k equals to 1. So I've just picked one simulation, but naturally I can do the same. I can run the same idea over multiple simulators. Each time I'll have nk number of times. For each kth simulation run, I'll have nk number of times state I appears in the trajectory. I can use that to estimate the cost for the mth time in the kth simulation, and then I can take the entire average, and that gives me an estimate of the v hat mu I. Okay, so that's one way. That's a more sample efficient way of estimating the value function for a given policy. Okay, so and that's what many platforms do. So if you go to Amazon, for instance, and you come up with, say, a policy mu, a recommendation policy mu, how will you know that your policy is better than the existing Amazon's policy? This is the algorithm you will implement, and you will check whether the value function out of your policy is better than the value function of the existing recommendation policy at Amazon or not. Okay, or for instance, Netflix and so on and so forth. Any questions so far? Does this sound reasonable?
You just incorporate the temporal difference from
Yeah, you will do it for every I. You will do it for every I. So, okay. So let's do it for 2. Okay. So we have done it for 1. Let's do the same thing for 2, just for getting our hands dirty and understand how this works. So let's say, what are the samples of discounted cost from state 2? T equals 1 to capital T alpha raised to T minus 1 Ct. What else? So 2, remember 2 starts from time t equals to 1. So T goes from 1. When is the next time 2 appears? T equals to 5. So capital T alpha raised to T minus 5 Ct and so on. Okay. So you can get estimate for all possible states 1, 2 and 3 using this trajectory. Does that make sense? Okay. Any other question? What is a problem with that method? Maybe not a problem, but anything you notice about the cost estimates that you're getting out of that?
I think it's problem is that, for example, when a state appears later, okay, it's an error becomes larger because we truncate after t.
That's right. So definitely you are truncating at t for sure. You're truncating the simulation at t, so this is not really a true estimate, and therefore you have some noisy estimate of the expected cost. Anything else that you notice here about the cost estimates? So in the previous case, we were starting from the same state and we were doing multiple simulation runs, and these were all independent of each other. In this case, I'm using a single trajectory in order to come up with the cost estimates, and now my estimates are correlated. Okay, so these estimates are correlated. Okay, so now what I'm saying is I'm going to use correlated random variables to estimate the expected value. Is this a good thing or a bad thing? Yeah. The variance becomes larger. Okay. Certainly the variance becomes larger, and you already did this problem in assignment 1, problem 1, right? So if you have correlated random variables and you're using some averaging using correlated random variables, you might have a higher variance than if it were uncorrelated. But I'm going to live with the higher variance. Why? Because I don't have anything better, any better algorithm to do. In order to come up with a better algorithm, I'll have to have 5 different worlds with 5 different New York Times website with 5 million people who will come to the New York Times website, and that alternate world is not possible for me. Okay, so I can't live in an alternate world, and therefore I have to live with a bad variance estimate of the value function. Any other question? Okay. Let's say we are not at New York Times. Let's say we are in Google, and we want to do this estimation. Okay, parallel. We want to have multiple simulators for the estimation. So what will you do? You have a policy mu, and you want to come up with different sample paths. How would you do it? So you know what you generally do is have cohorts of customers, right? And one set of customers you will show a specific policy, to other set of customers you will show some other policy, and then you can, by cohorting the customers, you can have multiple simulations with multiple policies or the same policies, and you can have independent samples from those multiple cohorts. So you can force independence in some cases if your traffic is high enough, but if your traffic is very low, or you don't have a sophisticated backend system to be able to have this cohorting situation, which is the case with many startups, then this is pretty much the only option you have, because you only get a single sample path. You get a single sample path of states and cost pairs under a policy mu. So in order to be able to do this multiple simulation, your backend has to be really strong, and that's what good big tech companies are good at. So just some tidbits of information that you might find useful if you were to work in those companies. Okay, if there are no further questions, I want to move on to TD lambda. Why does this particular thing converge? Why is this a good estimate? The answer is Wall's identity. Okay, so if you want to prove the convergence of this particular result, you need to use what is known as Wall's identity, and you get some sort of convergence guarantee as the number k, capital K, goes to infinity. So if you let k go to infinity, you have finite number of states. Each state is visited infinitely often in these trajectories. Then this particular estimator converges to the value function as capital K goes to infinity in probability, and that's proved by Wald's identity. Yeah.
So in the way that you wrote it here,
Yeah.
if the nk differ across k,
Yes.
you're giving them all equal weight in the sum.
That's right.
Why don't you bring in the nk that's now in the denominator into the numerator and put it between those sums? That way you're going to give them the correct.
That's a good question. I don't know. This is the algorithm people have used, and I'm sure there is some convergence proof for this particular algorithm, and that's why people are doing it. Yeah.
Okay.
Yeah. But definitely you can do that. So his point was, why don't I just do 1 over nk here and then divided by k? I guess that should also work, but I really don't know what sort of results you will get in terms of convergence guarantee. Okay, but certainly one algorithm to try. Any other question? No? Okay. Oh, I want to spend some time on trying to. So I want to spend some time thinking about this particular time capital T. Okay, so how long this capital T should be. So one way to think about capital T is, of course, alpha raised to T. The other way to think about capital T, and I'm not going to get into the math, but another way to think about capital T is going to be the mixing time of the Markov chain. Okay, so what is mixing time of the Markov chain? So remember this, once you fix a policy mu, this states that you are visiting forms a Markov chain. So let's talk about the mixing time of the Markov chain and how that influences the estimate of this cost that we are trying to estimate. So I'm going to do an experiment in the class. Well, it's a thought experiment in the class. So I have 4 glasses of water. Oops. Okay, and I want to mix sugar in the water. Okay, that's my goal. I want to make sure that the sugar gets mixed in the water equally in the entire water. So option 1 is I have cold water plus sugar. So I put sugar in the bottom and I just let it be. The second one is cold water, sugar, and I'm going to stir it. I have hot water, sugar, no stirring, and I have a hot water, I have sugar, and I'm stirring. I want you to think about or come up with some random guess of how much time it's going to take for the sugar to get mixed with the water. How much time in seconds or hours or minutes? So I'm doing cold water plus sugar but no stirring. How much time is it going to take for the sugar to get mixed in the water? I don't know, few hours. Okay, let's write 5 hours. I don't know how much time it's going to take. What about I have cold water, sugar, and I'm going to stir it? How much time it's going to take? I don't know, 5 minutes. I have hot water and sugar, but I'm not stirring it. How much time it's going to take? I don't know, maybe 20 minutes. Hot water, sugar, and I'm stirring it. It's going to take maybe 30 seconds. So depending on the policy, which is stirring versus not stirring, and cold water versus hot water, so that's your policy, that's your action. You have different mixing time of the Markov chain. So what's the Markov chain? What's the state here? The state here is how much sugar is in per cubic inch of water, right? Let's say that's your state space. So in this case, the state will converge to the steady state value after 5 hours. In this case, the steady state value will be reached in 5 minutes. In this case, steady state value will be reached in 20 minutes. In this case, steady state value will be reached in 30 seconds. Okay, so this number is known as the mixing time of the Markov chain. So mixing time is how quickly the distribution reaches the steady state distribution of the Markov chain. And depending on the different policy, you might have different, you definitely have different steady state distribution, but also different mixing times of the Markov chain. So if you think about, let's say there is a traffic signal, and let's assume that you have flushed the entire traffic signal, how quickly the Q length is going to build up in that particular traffic signal, right? So that's the mixing time. That tells you what the mixing time of that particular Markov chain is. You're standing at a Starbucks cash register. You have 4 registers, but only one person serving the employees. And then somebody comes in, flushes the entire queue. Now the queue length is 0. So somebody comes in, like all the 4 registers are working. All the people are able to place their order. The state starts with 0. And then you're back to one particular register. How quickly the queue length has started building up for that particular Starbucks. So you can think of mixing time for every different Markov chain. And what you really want, if your mixing time is very small, this estimate would be very good. If your mixing time is very long, this estimate would be pretty bad. Okay, so that's one way to think about how good this particular estimate. So this is just a way to, it's a hand wavy way of thinking about it, but it's a good way to think about whether this estimate is good or bad. So the way to think about whether this estimate is good or bad is to think about the mixing time of the specific Markov chain that is generated out of the policy mu that you have picked. Okay. Now, we have not talked about mixing times and so on in this particular class, so I won't belabor on this particular topic too much. But those of you who have taken probability theory, especially the measure theoretic probability in the math department, you can actually read some of the papers on how good this estimate is for a finite k, finite value of capital K, how good this estimate is, and it depends strongly on the mixing time of the Markov chain. Okay, so lots of papers have been written in the recent 5 or 10 years which studies the finite time performance of some of these algorithms. And so by finite time performance, what I mean is this capital K, like how many simulations you are running and how long, this capital T. So these are the 2 parameters that you pick, right? How many simulations you will be running and how much time will you be running each simulation. And the performance of these kind of estimates is strongly dependent on the mixing time. So that's an important observation, and I think you should, if you're interested in that topic, you should read those papers and get a sense of these estimates. Okay, any question so far? No? Okay, so let's talk about lambda policy iteration. So in lambda policy iteration, the idea was I want to make sure that I write the expression correctly. We have dk, okay, d of ij, c I mu I and j plus alpha jj minus ji. This is known as the temporal difference. And I was interested in computing delta of I to be expected value of summation t equals 0 to infinity alpha lambda raised to t and d it plus 1 given I0 equals to I. And then my j next was j plus delta. Okay, so this was in a nutshell lambda policy iteration. We talked about it maybe like 2 or 3 classes ago. And the idea there was I start with a policy mu and I have the estimate from the previous run j, and I want to compute the next estimate of j using this lambda policy iteration algorithm. So if lambda was equal to 1, this would be exact policy iteration, so I'll be evaluating the policy exactly. But if lambda is less than 1, then I'm not really evaluating the policy, but j next is approximately equal to v mu for lambda close to 1. That was something we talked about in the lambda policy iteration. Okay, now I want to do the same thing for the so what is known as temporal difference TD lambda algorithm. So in TD lambda algorithm, my goal is compute j next using simulation. Okay, so I want you to think about it and tell me how you would go about solving this problem. Let's assume we are still in 1990s. Okay, so 1990s is when TD lambda became pretty commonplace. Yeah, any thoughts? Any thoughts on how we compute this? How do we compute j next? So let's say my goal is, so I'm given a j, I can compute dt as ct plus alpha j it plus 1 minus j IT. So this is a sample of this particular random variable. Okay, so from this particular trajectory, I can compute the temporal difference. Sample of temporal difference. Okay, so whatever is here inside this particular expectation, I was able to compute a sample using the data set that's provided to me. What do you want to do? How do you want to compute this? So now we have seen one way to compute how to evaluate the policy. We're doing something very similar. Remember, the only difference there, so what I had written there was alpha raised to t, the cost function. Now I have alpha lambda raised to t, and instead of the cost function, I have the temporal difference. Okay, but I can use the same apparatus that I developed just now to compute this delta of I, right? So I'm going to look at how many times I appears in the sample path, and then from there I can do the computation of the temporal differences, which is delta I, and then I can add it to the current estimate of the cost function or performance index. I'll add it up, and then I'll get the next performance index J next, from which I'll then do the policy update. Yeah.
That's what's confusing to me is that this is all conditioned on I0 equals I.
This is all conditioned on I0 equals to I. That's right.
So there's only, when you have one path, you
yes.
only have one I0.
That's right.
Okay.
Oh, so this is the theory. In theory, you can do all of this computation for every I. Mm-hmm. Right? So delta is a function of I.
Right.
And for every I, you have to compute this expectation in order to compute delta I, and then you add it to the cost function and you get an estimate.
So my point is, if I only have a single path
yes.
that has a single starting state,
yes.
then it's not clear that I can chop that up into many subpaths and preserve this idea of the single starting state.
Actually, that's what we did in the previous algorithm as well. Yeah, we did the same thing in the previous one. So remember, we had this 1, 1.
Yeah. I guess that has to do with maybe the stationarity.
It has to do with the Markov property.
Yeah.
So once you are at state 1 and you're looking at the forward, everything that happens in the future doesn't depend on whatever happened in the past, given that you're starting from state 1 right now. So it has to do with the Markov property, that the future becomes independent of the past because of the Markov property of the state evolution.
Yeah, but somehow like there's still a link between what happened at time 0 and what happened at time t. Right?
Not quite, because of the Markov property. If you know what happened at time t minus 1, which is it minus 1 and ct minus 1, if you have observed it, yeah, then it doesn't matter what happened before it minus 1. Okay. Okay, so let's do so let me define these stopping times. So I have stopping times tau . So I have so let's assume single sample path, because for multiple sample paths, you will have to do the same thing for each sample, and then you will have to take the average. So let's do single sample path case. So I'm going to define tau k, tau I k equals to the time index t at which it equals to I kth time. So this is a stopping time. This is known as a stopping time, which is the time index t at which I visited state I kth time in that particular single sample path. Okay, so let's again look at an example because that will make it clear. So I have 1, 2, 3, 1, 1, 2, 2, 3, 3. So what is tau 1, 1? That is, okay. So this is C0, C1, C2, C3, C4, C5, C6, C7, C8. So what is tau 1, 1? That is equal to 0. Tau 1, 2. What's the second time state 1 was visited? 3. What is tau 1, 3? So what's the third time state 1 was visited? 4. Okay. Same thing I can do for tau 2, 1. What's the first time state 2 was visited? 1. What's the second time state 2 was visited? 5. And so on, right? So I can keep filling up this stopping time table and figure out at how many times, what's the kth time state I was visited. And then based on these stopping times, there are 3 different algorithms for computing delta. So first visit TD lambda. Let me write it here. My delta hat of I is given by summation t equals to tau I1 to infinity alpha lambda raised to t minus tau I1 dt. Okay, so what am I doing? I look at the first time instant state I was visited. I look at the entire sequence of dt that appeared after that. I multiplied it by alpha lambda raised to t minus the stopping time. Sum it up. That gives me my one of the estimates of TD lambda, this temporal difference function, and that's called first visit TD lambda. Now you might argue this is not sample efficient. Okay, we are not using this information and this information and this information and so on. So you come up with the second algorithm, which is every visit TD lambda, where delta hat of I equals summation t equals to tau I1 to infinity Okay, so what did I do? Now every time state I was visited, I compute the temporal difference sum starting from that particular time and I sum it all up. And then I think I also have to take a, let me see if I have to take an average or I don't have to take an average. I'm pretty sure we need to take an average. Oh yeah, so right, so I do have to take an average based on the number of times state I was visited. Okay, that gives me every visit TD lambda. Now, of course, if this is infinity, then of course you have to take some limit. You have to take some limit based on how many times that particular state has appeared. So maybe I should write it as capital T, and then I have to divide it by n capital T of I. So this is the number of times state I appeared in the t time step, and then I have to take limit t goes to infinity. So the way the book writes it is slightly different, so I'm writing it slightly differently. So this is the idea behind every visit TD lambda, and then you can come up with a recursive formulation to compute this every visit TD lambda, and that's the form that every book will give you for this particular algorithm. Okay, so each of this is a sample for the temporal difference function. So you pick all these samples, you sum it up, and then you divide it by the number of times I was visited.
So is that expectation over all possible trajectories starting?
Over all possible trajectories, yeah.
Okay.
Yeah. And then there is another one called restart TD lambda. So what does restart TD lambda say? It says that instead of going all the way to the end of the horizon, I'm going to stop this summation until I reach tau I of 2. Okay, so this one looks like summation t equals to tau I1 to tau I2 minus 1 alpha lambda raised to t minus tau I1 dt plus summation t equals to tau I2 tau I3 minus 1 Okay, so that's restart TD lambda. So you compute, you stop this computation at one step before I was visited again. So I was visited at tau I1, tau I2. So one step before, which is tau I2 minus 1, I'll compute this temporal difference term, then I'll restart the computation of the temporal difference term. And this one appears to be a superior algorithm in practice. Okay, so this algorithm is superior in practice. I think the reason why it is superior, although I've not seen a proof of it, I think that the reason why it's superior is because all of these are uncorrelated, right? Because you're stopping the, remember, if in this case, all of these samples are correlated samples. Here we are uncorrelating the samples at the expense of not computing the infinite sum. And for some reason, this one gives you a better estimate of the temporal difference than this particular algorithm. Yeah.
You're taking an average.
You're still taking the average. Okay. Because each of this is a sample of this expectation, right? So this is an average of this expectation. This is a sample of this expectation. And therefore, you have to take multiple such samples and then average over all the samples. Yes? Sorry? Very good question. So the question is dt Markovian or not? Anyone wants to answer that question? Is dt Markovian or not? So it turns out that dt is a function of a Markov chain, but it's not a Markov chain itself. Okay. Any other question? Yes.
So for this T lambda algorithm, how can we iterate the lambda in different algorithms?
No, lambda you can determine through trial and error. That's the only way to know whether TD lambda is working or not. So a lot of these are known as hyperparameters of reinforcement learning algorithm. And the hyperparameters are not something that somebody can tell you that this is the hyperparameter that will work for this particular algorithm. You try and error, yeah, exactly. So you go to Netflix, you try and error, you figure out the lambda for Netflix, then Amazon hires you, then you try to use the same lambda for Amazon's problem. If it works, great. If it doesn't work, then you change lambda and then you get hired by DeepMind. And then you use the same lambda for DeepMind and maybe it works, maybe it doesn't. Any other question? So in this particular, so one comment that I want to make here is the way I have written these algorithms, you need to have the entire sample path up front to be able to compute each of these terms and to be able to compute this delta hat. Okay. What will happen in practice, you can create a version of these algorithms that you can run online in an online fashion. So you don't have to wait for all the samples to be collected in order to be able to compute these delta hat. So those algorithms are given in the book and people call them online algorithms because you, as data is getting collected, you can keep updating the delta hat. So remember, dt you can compute as data is getting collected, you can compute dt instantly because it's just the sum of these three variables. And then you can come up with a way to update this delta hat so that you're using the samples progressively. Okay. So those algorithms are difficult to write on the board, so that's why I'm not writing. But you know, the book, this book by Bertsekas on neurodynamic programming contains how to convert these algorithms into an online algorithm where as the samples are getting collected, you are updating your delta hat.
I have another question.
Yes.
So for the homework, we are also for TD lambda, we need a trajectory.
That's right.
And I think in our homework, we are asked to use TD lambda, but we are not only give a translation matrix.
Yeah, so that's not TD, that's lambda policy iteration. So you're able to compute this exactly in that because the transition kernel is given to you, right? So you know exactly what the probability of IT to IT plus 1 is in the homework, right? Because you have that matrix. So you can compute this expectation exactly. Okay. Any other question? Okay. You've not yet implemented this sample-based algorithm. So that's coming up. That's homework 3. Okay. So you will have samples, you will generate samples, and you will use those generated samples to compute these values. Okay. All right. So one thing that I wanted to, so one of your friends rightly pointed out that dt is not a Markov chain. It's a function of the Markov chain. And remember, we were talking about mixing time of the Markov chain. So if you think about it, why do these functions of Markov chain, summation of functions of Markov chain, why do they converge to something like this? You know what is the area that studies this sort of properties of Markov chains? Anyone knows? So just for your information, that's called concentration inequalities. Okay, so for those of you who are theoretically who are working on theoretical methods in reinforcement learning, this topic is very important. So one of the famous concentration inequality is Hofding inequality. And what's the idea in Hovding inequality? You have I0, I1, I capital T is a Markov chain. You have F0, F1, Ft functions of Markov chain. Functions on the state space S. And what does Hovding inequality studies? You know, last time when I was teaching this course, which was in 2020, I had not made this connection. But since then, a lot of people have studied concentration inequality. So when I read the paper, I realized that there is a connection between Hovding inequality and some of these methods we are talking about. So what does Hovding inequality studies? It studies what's the probability that summation of Ft it t equals 1 to capital T minus expected value of the summation t equals to 0 Ft it greater than T epsilon is less than equal to delta epsilon. So you have sum of Markov chains, you have the expected value of the sum. How far are these? So this is a sample, right? And this is an expected mean, expected value.
Is there any absolute value?
Sorry?
Is there any absolute value?
You can put an absolute value, or you can look at less than minus T epsilon. Yeah, so you can study both of those properties. Yeah, I mean, you can put an absolute value, or you can study it without the absolute value. But anyways, so this sort of inequalities are studied under the umbrella of what is known as concentration inequalities or Hovding inequality. And people tend to study, if you sum functions of Markov chains, you subtract the expected value of that sum, what's the probability that these two differ by greater than T epsilon? And they try to find this concentration bound, okay, delta epsilon. There are lots of papers written on this. So if you look at the area of concentration inequalities, you will see hundreds of papers by now. And this idea is essentially very useful here, where you are trying to have functions of Markov chain. So remember, we just mentioned that dt is a function of a Markov chain. So as long as the Markov chain has certain desirable properties, which is its mixing time is very small, you can actually come up with a bounds on what's the probability that delta hat minus delta is greater than epsilon. Okay, so that's just for those of you who are looking for research problems, who want to investigate stuff in reinforcement learning. This, as of today, this is a very hot problem in the reinforcement learning area, which is to come up with Hovding inequalities for special classes of Markov chains, and then study the concentration bounds for these class of algorithms. Okay, so people are studying concentration inequalities for TD lambda, concentration inequalities for approximate reinforcement learning, and so on and so forth. So just something to keep in mind if you're looking for problems, especially those of you who might be looking for reinforcement learning projects. This is also a very good project to work on, which is depending on the Markov chain, how quickly would delta hat converge to delta, and what's the sample complexity in order to get within the epsilon bound with high probability. Okay, any questions on that? It may not be useful for other people who are not working on reinforcement learning, but for people who are working in reinforcement learning, it's an important topic to study.
So it's
Yes.
convergence in capital T. It's
Yeah, so how much capital T? What is a capital T so that delta hat is close to delta with high probability, right? So capital T is in some sense the sample complexity of the reinforcement learning algorithm or TD lambda algorithm. Okay, wonderful. So we have done policy evaluation. We have done Q-learning. We have done empirical dynamic programming and empirical value iteration. So we have pretty much touched upon a lot of simulation-based methods. In the next class, we'll talk about multi-arm bandit, which is a very special class of reinforcement learning algorithms. And we'll talk about regret bounds for multi-arm bandit. There's a course on online optimization, which is being offered next semester, again in ECE department. I don't remember the number of that particular course, maybe 8101. So that course will be taught by Professor Attila, and he's going to spend significant amount of time on multi-arm bandit. So I am not going to spend significant amount of time on multi-arm bandits. So there will be like one class on multi-arm bandits, and then we'll move on to more sophisticated reinforcement learning algorithms. So thank you so much, and I'll see you in the next class.